So again, the true posterior is in black, is the black contours. The analysis ensemble that comes from ANKF has moved the particles into a region of interest, but it does not exactly represent the target. Okay? So that's the failing of the ANKF. Okay? But it has moved the particles into the region of interest. So now we can sort of maybe summarize that. Well, so the ENKF, what happened? Well, the ENKF is intrinsically biased. By restricting ourselves to linear transformations, we will not converge to the true Bayesian solution. Okay? Because we saw the true Bayesian solution, it would put if you wanted an unweighted ensemble that represents the posterior, I ought to have a lot of particles in this mode, a lot of particles in this mode, and not so many here. The ENKF gives us something different, but in practice, for many practical systems, it does a good job of tracking, its mean tracks the truth reasonably well. But it's not good at representing, for instance, this bimodal distribution. So it is biased, more generally. It will not, if I generated more particles, I would essentially have the same problem. So that's sort of a little bit dissatisfying. From a UQ perspective, then, there are really no guarantees on UQ. So one sort of, this is sort of a truism. Just because you have an ensemble, just because you have a distribution, doesn't mean that the distribution means anything. And I have an ensemble, and the ensemble has some spread, and maybe I can look at its variance, but does that have anything to do with the actual covariance of the posterior? Maybe, maybe not. In general, the ENKF sort of provides no guarantees on UQ, and there's a nice paper by Andrew Stewart and Cody Law a couple years ago that sort of did a full force, MC Bayesian solution of a smoothing problem and compared that to ENKF and a bunch of other algorithms and evaluated the differences. Nonetheless, you have to kind of respect what the ENKF is able to do. It's able to track the state reasonably well. People have used it in far, far larger scale applications, far more operational systems than anything like a particle filter. So we shouldn't throw it out. We should think about, what are some issues, what are the things that we could maybe make better. So some questions are, for a given ensemble size with an ENKF, are we doing the best that we can? Can we sort of mitigate this issue that as I increase the number of particles, I may or may not necessarily do better? And maybe the larger question I want to ask is, could we actually get closer to the Bayesian solution while preserving some of the robustness of ENKF approaches? Okay. And I want to sort of philosophically say that I want to answer these questions in a situation that is kind of computationally limited, where I'm not going to be able to draw 10 million ensemble members. I'm going to be limited to maybe, I'll say hundreds, and you'll laugh at me if you're a practitioner and you'll say 20, but I'll say hundreds for now of ensemble members. And we're kind of limited by computational resources in terms of how close we are ever going to get to the Bayesian solution. But given a sort of a certain fixed number of particles, could you get closer to it? Could you step away from the sort of limitation of linear transformations that ENKF has? So the approach I'm going to talk about today is close in spirit to something that's proposed for very low-dimensional systems, the rank histogram filter from Jeff Anderson and Snyder and others. But we're going to sort of marry this with some new ingredients related to coupling and transport and non-Gaussian Markov random fields that will let us extend these kinds of ideas of nonlinear transformation filters to higher dimensions. So here's kind of the problem setting that I want to consider. I want to consider the filtering. I'm going to focus most of the talk from now on filtering of state-space models with high-dimensional states, nonlinear dynamics that are challenging, for instance, chaotic, as we saw in the opening talk, transition kernels that are intractable in the sense I'm not going to presume that I can put my hands on pi of zk plus 1 given zk, that I'm not going to be able to say evaluate that density or take its gradients. So I'm kind of taking off the table variational approaches, 40 var, things like that, which is a whole other line of work, and I'm not going to talk about that. I'm just sort of, based on our limitations that I'm setting up for this problem, let's say we can't do variational methods. That can actually be very nice. I have a limited number of model evaluations. So all I can do is essentially draw samples from this forecast ensemble. In other words, I can take samples from a previous filtering distribution, apply the dynamics, march forward a time step. I have a forecast, I have some observations, and now I need to figure out what to do. The number of samples that I can draw is going to be relatively small, and I'm going to assume I have observations that are relatively sparse in space and in time. Okay? So these are kind of typical challenges. These aren't just entirely made-up challenges. I think these are maybe typical challenges that are faced in numerical weather prediction, or geophysical data assimilation, but on the hand, you guys are the experts in those things, so you should tell me if those are typical or not. So in this setting, state-of-the-art results in terms of tracking are obtained with various flavors of ENKFs. Okay. So the main idea I want to discuss here is, okay, I like the idea that the ENKF moves particles into the regions of interest. I like this, so essentially this idea of transforming the forecast ensemble into the analysis ensemble using some kind of mapping is very attractive, and it avoids things in taking away things like weights, which inevitably lead to particle degeneracy, also seems attractive. So what we want to talk about is, can we actually sort of preserve this notion of transforming the forecast into the ensemble into the filtering distribution, but using nonlinear transformations? And how can we construct those kinds of nonlinear transformations? And how can we actually do that in a tractable way given limited numbers of samples? So what these two bullets may not mean anything yet, but this is kind of the main idea that I'll illustrate for the rest of the talk. Essentially what we're going to do is sort of two steps. We're going to take the forecast distribution and the filtering distribution and say in general these are distributions on high dimensions. We can't hope to represent them exactly with the limited number of samples. We're going to regularize the problem by projecting onto some manifold of sparse, non-Gaussian Markov random fields. I'll describe that. And we're going to introduce local nonlinear features in kind of a stable fashion. So what we're actually going to introduce is a filter that reverts to the ENKF as you relax certain assumptions and as you take away certain nonlinearities. So to build this up, we need a couple ingredients. So if you're sort of bear with me, I'm going to go on a couple digressions and build up a couple mathematical ingredients that we're going to combine back together to design this filter. So the first ingredient is the notion of a Markov random field. So if you come from machine learning or computer science or things like that, this might be, or spatial statistics, this might be a familiar concept. This is basically a way of understanding conditional independence relationships among random variables. So suppose I have n random variables, z1 through zn. This might be the value of the state of my system at different points in space, for instance. If I'm thinking of like Lorentz 96, that might be sort of each of those 40 coordinates in the state vector. So I have this collection of random variables. Let's say just real valued random variables. They have some joint density that's strictly positive. I can associate with this collection of random variables a graph. And the graph encodes conditional independence relationships. So what does that mean? The absence of an edge in this graph, so each of these nodes, first of all, represents one of the random variables. So here I have 6 random variables. If 2 nodes are not connected, so in other words, if this ij is not in the edge set, then those 2 nodes are independent, conditioned on all the other nodes. Okay? This is the notion. This is the mathematical notion of conditional independence, and I denote it like this. So zi and zj are independent, conditioned on all the other nodes in the vertex set. Okay? This map is called an IMAP. It's an independence map for the distribution pi, and essentially describes the conditional independence relationships that this distribution has. So how do I come up with a map? Well, in general, this is part of the probabilistic model. So from a probabilistic model, I can write a sort of graphical structure. There are some relationships actually between the notion of an independence map and Hessians of the log target density. And this maybe makes a bit more sense if you just can restrict yourself for the moment to the Gaussian case. So if you give me a Gaussian density, and I look at the log of that density, and I take second derivatives of it, essentially what I'm doing is picking out elements of the precision matrix of the Gaussian, the inverse of the covariance. And where the precision matrix is 0, I have a conditional independence relationship. Okay? So sparse precision matrices in the Gaussian case lead to sparse Gaussian Markov random fields. But this result is actually more general to the non-Gaussian case because now this is a matrix valued function. So the Hessian of log pi, the matrix valued function. If it's 0 everywhere in a particular entry, then I have a conditional independence relationship in the non-Gaussian case. Okay? And you can actually use this to learn graphical structure from samples and do things like that. But for the moment, I'm going to assume that either we know the graph or we impose it actually as a regularizing assumption. Okay? And by imposing things like this in a regularizing assumption, actually saying something, maybe more physically what I'm saying the probabilistic interactions are kind of localized in some way. So this is kind of like localization, except in the sort of Gaussian setting, what we're doing is applying it to the precision matrix, not to the covariance matrix. And this extends to the non-Gaussian setting as well. So that's one ingredient. Second ingredient is the notion of, so why do we need the second ingredient? So we have this notion of conditional independence. We have Markov random fields. In general, I'd like to be able to represent and compute with non-Gaussian Markov random fields. And this is a bit more challenging of an object. People have dealt a lot with Gaussian Markov random fields, and you can represent them nicely with basically precision matrix and mean and things like that. But in the non-Gaussian case, we need some more sort of sophisticated tools. And the tool that I'm going to use is the notion of a coupling between probability measures. And so this is kind of the second key ingredient. And the idea is as follows. Suppose I have some distribution pi that I want to characterize that's in general non-Gaussian. One way, so if I wanted to, for instance, draw samples from pi, things people typically do, well, they might run MCMC, they might do some importance sampling, they might do a variety of things. An alternative that's related to those things is to say, can I actually couple pi to a very simple tractable distribution that I'm going to note by eta? So you can think of eta for the remainder of the talk as like a standard Gaussian distribution, zero mean identity covariance. Now, if I could find a map T that took samples from the standard Gaussian distribution and transformed them in a way so that I got samples from the target, then I would be very happy. And I'm going to write that sort of mathematically as T with the subsharp notation. So T pushes forward the standard Gaussian distribution to this non-standard target distribution pi. Essentially means that if I operate T on samples from here, the resulting samples will be distributed according to pi. I might also be interested in the inverse of T, which I'm going to call S, and I'm going to require that T be invertible. And the inverse of T essentially is going to take samples from pi and transform them back to a Gaussian. It's going to Gaussianize the complicated samples. Now, this would be a nice thing to have because if I wanted to generate samples from pi, all I need to do is generate samples from a standard Gaussian, which I know how to do, and evaluate the map on them. But more generally, you can actually think about T as a way of characterizing a complicated distribution. So rather than, say, writing down the density of pi, or rather than trying to run some sampling scheme for pi, I can say pi is the distribution that is represented by a particular map T and a particular reference distribution eta. It's a way of characterizing this distribution that I want to operate on. Okay. Now, one thing you might ask is, well, when does T exist, or in its inverse, under what conditions, so on and so forth. This relates to the notion, actually going all the way back to the 1700s, of optimal transportation. So first of all, these maps exist under pretty weak conditions, and if I'm assuming there's no kind of atoms or delta functions embedded in my distributions, then the maps will exist. There's an infinity of maps, though, under most conditions. Now, people have thought about, what's maybe an optimal way of taking probability mass and eta and rearranging it to give you pi, and optimal in the sense that maybe minimizes transportation cost, minimizes the amount of warping that needs to be done. That leads to notions of optimal transportation, where you pick a cost function, little c, which has a lot of nice properties, but this is numerically challenging to solve in general. So we're actually not going to deal with optimal transportation. This is just for context. The map instead that we're going to use for most of our developments is this triangular map called the Noth-Rosenblatt rearrangement. And this triangular map looks like this. So again, these are presumably, so presume I have a density on Rn. This is a map. This is a function from Rn to Rn. And it's lower triangular in the following sense, in the sense that the first component is a function of only one variable, the second is a function of two variables, all the way down to the nth component is a function of all n variables. It turns out this map is just general enough, this triangular form is just general enough to represent relatively arbitrary distributions. And it has a lot of nice features. So the Jacobian of this is a lower triangular matrix. The determinant of that is easy to evaluate. It also kind of exposes marginals in an interesting way, and it's going to enable conditional sampling in a useful way. So we're going to use maps like this to represent non-Gaussian Markov random fields. Okay? In other words, we're going to say, presume that we have a reference distribution that's Gaussian. I have this nonlinear transformation of that reference distribution, and it's going to give me some non-Gaussian distribution that I can then do things with, draw samples from, extract conditionals from, so on and so forth. Numerically, we need to represent these maps in some way. So the various numerical approximations one could consider. One that we found to be pretty useful is this kind of integrated parameterization that guarantees monotonicity of the map. So this guarantees that the map T, that the kth component of the map is a monotone in its kth variable. Okay, just by embedding it in this. But that's kind of numerical detail. I'll not sort of bother you with that too much. Okay, so I put up two ingredients so far: Markov random fields and this notion of transport maps. And what's the relationship between those two? So it turns out the relationship between them is one of sparsity. And you can sort of essentially think of as follows. So rather than considering the map T, I'm going to, for the moment, think about the map S. And the map S is the inverse of T. S is the thing that takes samples from the complicated distribution and pulls them back to the Gaussian but the maps are invertible, so these are essentially equivalent objects. What I'm going to consider now is the sparsity of this map S. So S is in general a lower triangular map. But if pi has some Markov properties, so if the I map associated with pi itself is sparse, then what I can say is that the map S itself inherits that sparsity, inherits some of that sparsity. Okay? So to kind of paraphrase the theorem, the Noeth-Rosenblatt rearrangement, which is a nonlinear function, inherits the same sparsity pattern as the Cholesky factor of the incidence matrix of that graph, the graphical model for pi, the I map for pi, okay? Provided that the reference is a product of its marginals.